Until you have genetic manipulation that will allow for near 100% conversions, then those kind of somatic therapies really aren't going to have any utility. It's very different when people propose to take T cells out of the bone marrow, put in something new and reinfuse them, because now you've created new immune effector cells that will go off and do their thing just like other T cells. And they could have long-lasting effects for many, many years. But that issue about somatic change, cancer is one of the hardest, because if you don't get 100% of the cells, 1% that survives is enough to come back and finish the job. Now it's different if you've got a metabolic disease. So if you had a disease of the liver, for example, and you could correct even 10% of the hepatocytes, you might be able to reverse the phenotype of a genetic disorder. So you have to really think about what fraction of the cells you need to actually convert. That's going to be one of the big areas for CRISPR in the future to deal with. But anyway, right now we want to talk about NGS capture methods. And so why do we care about this? Well, NGS is just totally revolutionized sequencing. When I was a graduate student, I sequenced T cell receptors by Maxim Gilbert, P32-based methods. In 3 years, it was a heroic effort, and I did 20,000 bases. As a postdoc, one gel of an AB373 did more sequencing than I did in 3 years as a grad student. So enough to bring tears to your eyes. And then, now today, one run on a mice in unbelievable amount of data. But even so, you're not going to want to sequence whole genomes, because it's just going to be too expensive. And the other part of it is you've got the data and you don't know what to do with it. And one of the problems that's always present in medical sequencing is the burden of unwanted data. You've got information that you don't know what it means, and now you've got to deal with it. And so one of the things that's important is to focus your questions. And there's two reasons for that. One is that you only get answers for questions you want answers to. The other is that cost and throughput. So if you have X amount of sequencing space, you can do 50 exomes compared to one genome. And if you're beginning to look at oncology type questions, you're not talking about germline mutations, which are usually going to be 50-50. You're talking about events that may be present in a cell population at 1 in 100 or less. And to do that, then you need to have depth of sequencing. So you don't need 10x, you don't need 30x, you need 200x, you need 500x sequencing to tool down deep enough into the sequence space so that you can really have any assurance that you're catching some kind of rare mutation. So how do you enrich? How do you narrow down the sequencing space so you're only sequencing the stuff you care about? And pretty much there's only two ways to do it. One is going to be capture, the other is amplification. So in amplification, you use the PCR-based method, whether or not that involves a MIP-type haloplex ligation event followed by amplification, or just PCR-based things, where you throw in a multiplex reaction and PCR amplified some fraction of a genome. And it's the easiest way to do it. Anybody can do PCR, and frankly, anybody can do that. It works well on small inputs amount of DNA, which is very friendly. It also is going to miss a lot of stuff. Because, especially if you're working in cancer, you're going to have rearrangement events and things. And if the two primers don't lie right where you expect them to, you do not get a product. And so you will be missing things by amplification-based sequencing. It's not theoretical, it's unavoidable. And the question just is, does it matter for your patient? Does it matter for this scenario? And you're not going to know. So there's going to be areas where amplicon-based is good, and it certainly is easy. But capture has the benefit of pulling down everything within a more of an unbiased way. And how does capture work? Well, capture is going to take a library fragment, so you've got a piece of genomic DNA here, and it's going to have target sequence you're interested in, It's going to be linked possibly to junk, which could be repetitive elements, which are mischief. And it's going to have universal adapters on the end. And the way a capture-based reaction works is you're going to have some kind of a DNA bait, a hybridization capture probe that's going to bind on it. And it will bind to this chunk of DNA, and it will bind to this streptavidin magnetic bead. You'll fish it out, wash it, and other stuff will wash away. Now, to make this work well, you've got to block binding events of the other stuff. You've got to block repetitive elements, and you've got to block adapters. We'll talk about that later. But the first thing is this capture-based piece. And the beauty of this is it's an oligo. And so if this happens to be next to a translocation fragment, it'll drag it down too. So you can find pieces of viruses, you can find translocation events, you can find all kinds of interesting things this way that you aren't going to find by PCR. The drawback is that it's a slightly more complicated workflow, and it's a little bit more expensive to get a hold of the probes for something like this. Now, right now there are sort of two general strategies to do capture. One is using oligos that are made on arrays that you can't QC. So you can make 100,000, a million oligos on an array, and then cleave them all off and make libraries out of them, make capture pools out of them, all kinds of things you can do out of them. But oligos made on arrays aren't as good as the oligos you can make on a single column. And also, the biggest thing is you cannot QC them. You have absolutely no way of knowing if an oligo was successfully synthesized on a chip, or how much was made. And we can tell you by looking at synthesis that's not on a chip, that synthesis sometimes fails. And yields between reactions vary. And so here you're going to have absent probes and probes that may be present at 5 or 10x different concentrations than you desire, and you're never going to know it. So our approach to this has been to use our ultramer-based platform to make capture probes. And ultramers are just oligos, but they're oligos made on a platform that is optimized for very high efficiency coupling that enables long oligosynthesis. So your standard oligosynthesis is probably in the low 99% range. And 99% efficiency sounds pretty good, right? But if you think about it, 0.99 times 0.99 times 0.99, 120 times, and it's not too long before you don't have all that much full-length product around. The enzymes in your body, your polymerases, have an efficiency of what, around 10 to the minus 7? So 10 to the minus 2 is actually kind of bad. For a chemical reaction, it's fantastic. But for making long DNA, it's not so good. Now our ultramers, we've changed the support system, the chemistry mix, all kinds of things about synthesis, and it's driven the coupling efficiency up to a reliable 99.6%. Now that 0.5% doesn't sound like that much, but that's the difference between tracking along this line for purity versus tracking along one of these lines. And so what it enables is synthesizing 120mers, where you're going to have at least 60% of the oligos from every synthesis are full length. And so the quality is there that you can use these things without purification. And this is what they look like. This is mass spec of a 120mer that's 78% GC. And you can see that we can easily assess the quality of it and know if the oligo is good. And if it's not good, it gets thrown out and remade. So you're never missing a probe. And this is the actual fail rates based upon our mass spec criteria, which are pretty stringent. But you'll see that, out of making, this is probably a 118,000 probe library that we made here, that, somewhere around 7 to 8% of the probes fail in the first synthesis. And we remake them, and then they're good. And so these things will fail at that same frequency on an array, and you'll never know it and can't do anything about it. To compensate for that, the way that you work with arrays is you heavily tile. And so you do many little step overlaps and try to over-synthesize, hoping that, you know, if this one fails, at least this one works. But you don't know that. Whereas for what we do, since everything is not only QC by mass spec, but you can measure an OD and normalize mass yield, you can tile end to end, and it works just as well as doing this kind of thing. So we've got an online design tool that will allow you to input a sequence, and it will array out the oligos for you to make these kind of pools. It will find repeats and mask them. And if you want it to be higher density than 1x tiling, you can go up to 2x with that. And some people do that if they're expecting areas with high frequencies of recombination. But otherwise, if it's just in a normal stretch of DNA and you're not expecting that, we think it's kind of a waste of money to tile more densely than 1x. So making custom panels now is expensive, because obviously it's going to cost a lot more to make 1,000 oligos than to make those oligos on a chip. Where it actually becomes cheaper is if you have to ask yourself, how many times am I going to use it? So if you've got an academic project and you're going to look at 30 samples, making a custom panel by oligos, forget it. It would just not be possible, way too expensive. But if you've got a big study going and you're looking at 1,000 samples now, it actually is cheaper to make it this way, because each synthesis produces so much oligo, you can make a lot of captures. And so for the companies that are doing medical resequencing, or the large university hospital labs that are doing medical resequencing for oncology, that are going to easily do 10, 20,000 samples a year, it's actually far cheaper to use these kind of panels. Now, to make these kind of panels more usable for people, we've made pre-made panels. So we've made a full exome, which is probably the single most useful thing. A separate AML panel, a pan-cancer panel, and an inherited disease panel, which is about a quarter exome. And since these are already pre-made and pre-aliquoted, then the costs are reasonable. And they're very easy to use, and this makes entry into academic labs now a lot more feasible. The other thing you can do with these things is you can easily change content. We'll get into that in a minute. So let me just sort of show our development process for this. Our first development with this started with Foundation Medicine quite a few years ago. And they were working on developing a commercial oncology test to be done on FFPE. And their first set was a 1.1 megabase adjuvant set. And they were having parts of that they just could not capture reliably. So what they wanted to do was see if they could spike in our kind of probes into that set and fix it. And here's what I mean by that. So here was their custom panel off the array. And you can see here was good density of sequence data, but this area had poor coverage. You spiked in the lockdown probes, and now suddenly you've got great density of sequence data at both locations. Well, when they saw just how much better this worked than this, they thought, well, why don't we just make the whole set that way? And this was the result of coverage. So if you look at the read depth, based on what they saw was we had a much more uniform read depth with no fallouts compared to the array-based set. And there were just this chunk of stuff that is very difficult to capture and to read. And if you look at that based upon GC content, it falls out that the area that's poorly captured is the high GC areas. So why is that? There's actually a very sound scientific explanation for this. And it goes down to basic nucleic acid thermodynamics. Most people think that RNA has a higher TM than DNA. But it depends on what you're capturing. An RNA-DNA hybrid can have a lower TM than a DNA-DNA hybrid. So this sequence here, these are the actual TMs. So this sequence as an RNA binding DNA has got a TM of about 72. The same thing, DNA is 80. What's always true is that RNA hybridizations are very high TM. So this as an RNA event is real high. The fallout from that is in long probes. If you've got hairpins from the RNA probes like you get with Schurzelein, you get these RNA hairpins that are so tight that they can't capture DNA. And that's why these kind of probes can't deal with high GC areas, is because the high GC areas form hairpins, the probes then yield to themselves, and then they don't capture the DNA targets. And if you want to read more about this development work, the whole first development program done at Foundation Medicine was published in Nature Biotech in November of 2013. And we've had a number of groups now working with their own custom panels that are finding the same kind of thing. That an array-based set made by Genoptics had a fallout at high GC levels. And here's with a different DNA input, you again see asymmetric distribution. Whereas with these kind of baits that are made off the Ultramer probes, you get much more uniform coverage throughout the entire spectrum of GC regions. Another area where that's becoming more important is that for medical resequencing, it's becoming more common today to also build in enhancer regions. And enhancer regions are usually GC islands. And so you're now increasing the number of areas that have high GC content. And so here is a capture difference between found at the Washington Genome Institute, where they built a new set of spike-in probes for enhancers, between the lockdown probe approach and here was array oligos from Imogen. Here's another example of that from Foundation Medicine, where it shows using RNA probes the coverage they get across this region, whereas with our DNA probes, the kind of results they get. And oftentimes these areas where you're beginning to see tumor translocation events are areas where you have unusual DNA structures or things that complicate capture. And we're finding that these kind of probe libraries are actually capturing these highly enriched translocation areas better. The nice thing about that is that you can spike them into sets. So instead of having to make an entirely new probe library, if you want to add content, all you have to do is make the additional probes and then spike them into the old library. And so I think some of that's enabled by the fact that you get so much mass yield that you've got plenty of material to work with and you can always just spike more into it. And so adding new gene content is fairly inexpensive, and in fact only takes a week. You know, you decide you want 10 more genes to put into this pool, you order the oligos, and a week later you got them and spike them in, and it's done. The benefit from having this really nice uniform capture process is that it is now allowing for almost reliable CNV detection. So you're getting some copy number variation assessment. So you can now see on the sequencing traces areas where you've got deletion events or duplication events. And that's traditionally in enrichment process has been difficult to do because the uniformity of capture hasn't been good enough to allow really good CNV calling. But many of our customers with their custom pools now are actually doing CNV calling with these sets. Now, what I call the flagship for this from your standpoint is going to be the whole exome. because the exome covers, obviously, all the coding regions, and it also is the one that's going to give you the greatest depth of coverage of things that uses a base for spiking in other areas that you may be interested in. So you could start with that as a base, then add areas to it that are of custom interest to you. And this sort of shows that point of the uniformity of coverage. So this is the uniformity of coverage that we're seeing on the exome capture set. And you can see across the whole GC range that it's incredibly flat. And the actual sequencing coverage depth is a nice sharp spike. You know, what you don't want to see for that is a real fat spike, meaning that you've got such widely varying capture efficiencies. And what we see is a nice sharp spike, which means that the capture efficiencies are good enough that for any domain area, you can begin to start calling copy numbers. So here's this was the set we made for Emory University. And their pediatric genetics group there does a lot of work with inborn errors. And when they've got a child born that's got unusual features or some syndrome that they can't characterize, the first thing they do is gene sequence with this panel. It's highly enriched for genes that they consider likely suspects for inborn errors that aren't going to be fatal, and are now being used by a number of pediatric medical genetics groups. And there are similar panels provided by more than one source. And you can see the depth and uniformity, well, you can see the uniformity of coverage here across this one gene, MABEL2, from the inherited panel that we made for Emory, compared to two other competing panels. And you can see just the very different level of coverage that occurs from these panels. And based upon this now, we're getting a very high adoption rate at hospital genetics labs for using this kind of product for their sequencing needs. Now, nothing's ever perfect. And the best case scenario is to have a product like this, especially if it's expensive to start with, that you can modify. Now, it's easy to understand how you can add a gene, but you can also subtract a gene. And that's something that isn't obvious until you think about it, and then you're going to say, oh yeah, of course. And here's a case where we didn't design this panel, but a customer provided the sequences. And it was a small panel, under 8,000 probes. And the on-target efficiency was kind of poor. And upon deep study, we kind of figured out that they had a few probes in there. It was actually only 10 out of 8,000 that weren't properly repeat passed. And they were dragging down other stuff that they didn't want. And what we did was we made anti-baits, anti-probes. So we made complements to it. And if you spike in the complements at 3, 10, or 50x, you can get rid of those baits. And in essence now they're taken out of the solution function, even though they're physically still in there. And so the anti-baits were able to bring the function of that pool up into a more acceptable range for them. And here's a case that was kind of fun. We did this in my lab for one of our scientists, my best friend in the lab. Scott comes from a family with familial hypercholesterolemia, and his cholesterol was 450 untreated. And so they didn't know what their mutation was, so they took one of their pools and made probes for 3 suspect genes, spiked it into the probe, and did the family. And here's what they found. They found a point mutation in the LDL receptor that was present in mom, dad, and himself, but not his sister. And it just is, kind of drives home how simple this was, that from getting the idea to do this to actually being able to do the capture took a week. Now, you could also say, why not just make the 3 genes and use that alone? Well, you can do that. But one of the things that we found is really small pools don't capture really great. Because when you're beginning to capture stuff and drag it down, stuff sticks to stuff. And so things stick to beads, they stick to plastic, and small sets have very high noise. And so you actually get a lot better result by spiking a few probes of interest into a larger set. It comes out a lot cleaner. If you have truly small sets, that might be a case where you actually are better off doing amplicon-based sequencing. So let's go into some of the factors of how you can use these kind of tools and optimize them for your needs. One of the things is probe density. And if you've got a small probe set, and you're using, say 100 animals a probe per pool, you're going to have low on-target efficiencies. But if you begin to add additional probe, up to say 400 animals, you're going to really increase your capture efficiencies. If you've got a big pool, you don't need nearly as much probe. If each probe is present in a large set, now this is the genetic disease panel, 100 animals is all you need, and in fact you still got pretty good capture at 50 animals. So these are the kind of guidelines that we can provide that help people to use these things most efficiently. There's another thing that goes along to that stuff sticks to stuff thing, which is that if you're using dilute pools, that adding carrier nucleic acid will really increase your results. And that can be as simple as tRNA or oligo-DT. Oligo-DT is way too short to really make any difference of hybridization capture, but yet will bind to the sticky sites that are on beads and tubes. Here's another way to improve this. We made a panel looking at the Doria-Shorum Ashkenazi set. 64 genes, 127 probes. And if you just basically follow with this tiny of a capture set, a single capture process, your on-target frequency is pretty low. But if you simply do a double capture, that can be done in one day. You can take capture efficiencies up from here to here. And now this is a 48-plex of the Doria-Shorum panel run on a mycete. And this was only limited to 48 because that's all the barcodes we had in the lab at that time. And you could easily take this up to, 100 or 200 plex on a mycete. Another thing to think about is your fragment size. People don't really think a whole lot about their library construction process, but when you're mapping on target, you define a region of interest, and stuff that's not in that region you consider off target, but off target may be the linked arms. And if you just make your shear size or your enzymatic degradation size shorter, then your on target rate is going to go up concordantly. So, obviously then if you're doing Pulveris, as you make the fragment shorter, your on target, the amount of off target material goes down. And obviously, things like cell-free DNA and FFPE that are already sheared, small, will have higher on-target. Temperature of hybridization. Everybody that provides a Hive solution will give you a recommended temperature of hybridization. But if you're working with your own specific sets, you can change that. And as you go from low temperature to high temperature, your specificity is going to go up. And you can see if we go from 47 to 50 to 60 to 70 degrees, that the on-target rate just climbs. But you can't just blindly look at that and assume that's good. You've also got to look at your coverage, because what you'll see is that these lower temperatures, you're really nice and flat. But up here at 70, when you think that you're really getting great on target, you're getting that at the price of now being skewed based upon your TMs. And your AT-rich areas are now being captured poorly. So actually, for the panel we looked at here, you would say that probably the best results are at 65. Not quite as good on target here, but much more uniform coverage. Now, it's something that usually is glossed over. One of the simplest the easiest things you can do to improve your capture efficiencies and your on-target rates are to use the right kind of blocking oligos in your mix. Because your capture probe is going to bind that region of specific interest. And you always think, well, that's what we're capturing. But you're going to capture other stuff too. And the other stuff you're going to capture are daisy chain events that come from either having repeats binding to repeats. So you've captured a region here that you care about, but that thing you care about is linked to a repeat that brings down something else. And that something else is garbage. You don't want it. So you've got to block that. Right now, people are using top 1 DNA for that, commonly used. We're working on trying to get a synthetic top 1 that's going to have slightly better performance and greater uniformity batch to batch because it's chemically defined. But that's not quite ready for the market yet. But the other thing we have are the adapters. Now, people think a lot about repeats, but they forget that in fact adapters are present on every molecule that's in the library. Every piece of DNA has an adapter. And if it doesn't have an adapter, it doesn't get sequenced. And if it has an adapter, it can bind another piece of the library. So you've got to block that event. Now, the original blocking oligos for that are simply the same sequence of adapters. And sure enough, if we put in a whole lot of that DNA sequence, it will block it. But the problem is that nobody just sequences one sample. These things are all highly multiplexed, sometimes with over 100 different barcodes present. And the barcodes are different sequences. And they provide a domain that's sort of a gap in there that don't hybridize well, that change the TM and lead to more of these kind of events. So we tried to stop that by creating a new version of blocking oligos that had two different chemical changes in them. One is that we don't make a barcode specific for a barcode anymore. We put an inosine region there that's going to be good for any barcode. And then we put in TM enhancing chemical modifications into the ARMs. And as a result, the blocking oligos now will hybridize and bind to the adapters before adapter can bind to adapter. And it can totally block the daisy chain. And this is the kind of results we're getting from the genome centers with this product, is that standard adapters, standard blockers will block a lot of the events, but these new chemically modified blockers block far better. Because just based on their thermodynamics, a blocking event happens on these before the regular adapter hybridization event can occur. And here's another one that was done at WashU. Again, standard blockers and the new chemically modified blockers. Now, this isn't something we routinely advertise in the catalog, but it's something you need to think about is if you're using kits, your linkers come with a kit, and there's not a whole lot of thinking to be done with it. But if you're doing something novel or different, you may order your own custom adapters. Or if you're starting to set up a sequencing core, you may want to start ordering adapters yourselves and get them a lot cheaper than buying in the kit. And the biggest problem about NGS adapters today is cross-contamination. And it's something that people don't like to talk about. But here's the cold hard reality, is that if we make a reasonable scale synthesis reaction, there's 10 to the 17th molecules in that synthesis. If you have 1 part per billion contamination between preps in a lab, what's 10 to the 9th to 10 to the 17th? That's 10 to the 8th molecules of contamination. That's a lot of contamination. And so people don't like to talk about this, but you cannot make all these things in a room together or on shared equipment and have everything be totally pure. It's physically impossible. And so what you have to do is recognize that that's a problem and then adapt your manufacturing methods to minimize it. And we've created a HPLC purification process that has very rigorous column cleaning methods, which are quite different from industry standard, that give far lower barcode to barcode cross-contamination than anything that any of the other providers do. It's really, it's a pain, but NGS is force these kind of things. Another thing that's becoming now very common are having end-domain MIDs and things that allow for direct molecular identification of individual molecule MIDs. And most people will just make a MID area just by putting in some N bases. And of course, the most common way of making an N base is what we call a machine mix. And a machine mix is that you've got bottles of A, G, C, and T, and you give a squirt of each, and they all go down their little tubes and go out through the heads and into the reaction vessel. But the reality is that each one of these things doesn't travel at the same rate, the same flow rate. If you've got an A going into an A, there's nothing else in the line, and so it's clean. But if you've got A, G, C, and T going together, they get uneven mixing. So you can actually make your MIDs and your areas with these kind of molecular barcodes much better if you do a hand mix of an N, where you put all 4 bases on a 5th port and only send them together as a mix. And in fact, that N base can even be done so that it's balanced. Now, all the 4 bases don't have the same chemical reactivity. And for example, G has the lowest reactivity and T has the highest. So if you just mix all 4 bases equimolar, you'll have more G's, more T's than G's. And here's sort of an example. Here's looking at the base composition of a mid-domain in a NGS primer that was made with machine mix, and you can see the really variable amount of bases at each position compared to a hand mix, where this is a very, very uniform domain. Now this was actually not an NGS adapter. You can tell this is way too long for a MID. These are actually aftermarket libraries that we're making for other purposes, where you have much larger end domains. But we make so many things for these kind of purposes, like either protein evolution or aptamer evolution. And we've got the methods down to do these hand mixes where you get very, very uniform end-base incorporation. And so if you really want to make high-quality MID adapter ranges, adapters, always order a hand mix. So a lot of this stuff has been sort of basics of oligo stuff that you probably don't normally think about. And I'm hoping that walking you through this will make it easier for you to think about how to obtain these things in the future when you need them. But, you know, in sort of summary, if you're going to do target enrichment, 2 ways to go about it: amplification or capture. And which route you take is going to depend on what your needs are, how many samples you're going to process, what's the application for the samples, and usually one approach is going to make more sense than the other. If you're going to do capture and you're only doing a small number of samples, then have your custom panels made on arrays. It's going to be a lot more cost effective. If you're going to do a fair number of capture events, then really consider the lockdown approach. Because after you start doing enough samples, they actually become cheaper, and the quality of capture is far superior. And when you, regardless of what system you use, look at these chemically modified locking oligos. They improve every method of capture, whether it be Agilent, Immelgen, IDQ, whoever. Because everybody's got adapters, and these things work better. So anyway, that's sort of a basic tutorial of how these factors of oligosynthesis impact your adapters, how they impact capture in NGS. And I hope that was somewhat useful to you. So anyway, if there's any questions about that, please let me know.
Trying to put the 2 things together, the first and the second texture. If you want to take a targeted approach to find off-target activity of CRISPR, what method of targeted sequencing do you recommend? The amplitude-based or the capture-based to go after predicted off-target activity of CRISPR?
We do amplicon-based. Just because for using, there's two ways to hunt CRISPR off-target effects. One's going to be a biased, the other's an unbiased approach. For a biased approach, you're predicting the sites, you know where those sites are, and frankly, it's easier to make a small multiplex pool if you're just looking at 50 sites or something. So we actually do that with amplicon-based. As long as you're okay with the possibility that you may miss a few sites if your damage done to the site is bigger than, say, 100 bases. So as long as you've got primers that bind that are far enough away and your fragment's big enough, you can still get reliable evaluation of those sites. Then, of course, you've got unbiased detection of off-target events. And right now, for live cell work, I think the best method is GuideSeq out of the Young Lab. But my understanding is that there's a new sort of better unbiased CRISPR off-target effect sequencing for NGS coming out that's not looking at live cells, it's looking at the cutting patterns in vitro. And that both Young and Caribou have submitted papers to Nature Biotech right now that are under evaluation that give two different methods for doing that in vitro that give you a lot greater depth of penetration to off-target sites than do the live cell approaches. I don't know if I answered your question.
Any other questions?
All right, thank you.